I can zoom in a little bit. Okay, so thing to start off with is new prefix, new subnet mask, and the number of hosts per subnet. After you set the problem, you're tackling the problem from the point of view of how many subnets do we need. So it's you'll see in a little bit that we're going to look at it from a different perspective shortly. But for now, yeah, just come up with a new prefix, a new subnet mask that meets the requirement of 32 subnets. And then, how many hosts do you have in each subnet based on the number of host bits that are left. And feel free to ask a question or feel free to ask a question as we're doing it if necessary. Yes.
Can you just give me a hint where to start?
So where to start is that 32 subnets. How many bits do you need? In other words, which power of 2 up here will give you 32? And so whatever power of 2 that is, that's how many bits you're going to take from the host, which is the last octet. You're going to take those bits from the host, and they're going to be part of the network ID. And to figure out that, so that whatever number that is, you add it to 24 to get your new prefix. And to get your new subnet mask, okay, we're working in the 4th octet because the first 3 octets are going to stay that way. So to get your new subnet mask, you just put those bits down in the table here and add up the columns, and that'll be the value of the 4th octet of the subnet mask. And then however many bits are left that you didn't put down in this table, that's the number of bits that are left for the hosts per subnet. And so you just do your 2 to the n, which is how many 0 bits are going to be in here after you put your 1 bits down, minus 2 will be the host per subnet, 2 to the n minus 2. So I'll start in just a couple of minutes. So when I posted the Monday's Zoom, I also, well, it was already posted, but there was a subnetting Zoom that I did back during the COVID years, 2020. Subnetting hasn't changed since then. So I posted that as long. So probably more time than we spend out here. So if, I put that in the module 6 also, the link to that, if you wanted to get more of that. And I also, I don't know, last week or so posted an announcement that had some websites for learning subnetting and getting subnetting problems to practice with and stuff like that. Okay, so let's start off with our new prefix. Our new prefix is going to be
29.
Say again? 29. And you got that by
2 in a bit, so you add the 5 to them, 24.
right. We need 32 subnets. So we look at our powers of 2 and whatever the superscripts, whatever we're raising 2 to whatever power that is, in this case 5, that's the number of bits that we're going to be reallocating from the host to the network. So that means basically we're going to be adding 5 bits to this subnet mask to make the network now 29 bits, the network ID 29 bits long. And then we need to put those bits into our table, 5 of them. And that will give us the value of our new subnet mask by just adding up the columns with the 1 bits. And what is that going to be?
248.
48. And I'm just going to do slash notation here. All right, so that is our new subnet mask, new prefix. How many hosts per subnet?
24.
6.
6.
6. So how'd you get 24? Just curious. Not who's sure.
2 times, 3 times 2 times 2 times 2.
It's actually, it's just 2 times 2 times 2, which is 2 cubed. That's a better way to look at it. To find host per subnet, once all of your subnet mask bits are down, and you know that the first 3 are all, you know, 1, so we really only care about this 4th octet. So once we put our 5 subnet bits down, the rest are host bits. However many zeros there are, you just look and say 2, there's 3 zeros, so 2 cubed is 8. But then we got to subtract the 2 for the broadcast in the network. So that gives us 6.
I just mixed up the 3.
See, I lost that. Oh, okay, I see. 3 host bits. Minus
3 host bits. cubed.
minus the 2.
Minus the
Okay,
2.
got it.
2 in minus 2.
Okay, so and then let's go ahead and enumerate at least the first few subnets that we've created by doing this. So the first one is always your original network. Whatever, you know, you're starting with, oh, I'm sorry, with the new prefix, that's always your first network ID. So that's going to be your first subnet. Your second is going to be 201.23.100 dot what? 8. All right.
Sweet.
And I'm not going to bother with /29. They're all /29. Okay. Later, that'll change when we do variable length. But in this case, we're just, you know, same subnet mask for all the subnets. And then, you know, the next one, 16, and so on and so on. And we got the 8. And again, there's a couple ways to look at it. I think the most visual way is just to, if you've got your table, is just to look at that rightmost bit. And that's, you're going to be your increment of all your subnets. 0, 8, 16, 24, 32, all the way to 248. 248 will be your last subnet. It's counting by 8s. The other way to do it is say, well, how many, you know, addresses are there that are not network addresses, network ID addresses? Well, there's 8. We can't use 2 of them, but there's 8 total addresses there. 6 of them are host addresses. So, but that 8 also tells you what your increment is going to be. So however many, you can also just say, you know, how many host bits are there? And if there's 3, that means our increment's going to be 8. If there's 5, that means our increment's going to be 32. If there's 7, our increments can be 128, and so forth.
One question. That's, you know, /24 to get to 29. I just forget how we get there.
Based on the fact that to get the 32, we did 2 fifths. And that 5 represents the 5 bits that we needed to
That you
reallocate, and we just add that 5 to our original
So you
original
just
prefix.
activate. Gotcha.
We just extended our subnet mask by 5 bits is another way to look at it. I'm going to open that door and try to get some
Yeah, it's hot.
breeze into it. I don't know why. Got the
I was on the right track.
Yeah.
Lost me.
It's really. Exactly. It's one.
Just like plug and play, like once I just figure out the formulas.
That's what I was thinking. I know that. It's like, why am I?
Call Sunday.
The addresses we can't use are 201.100.0 and 100.7.
So basically,
Yes, right. You can't use 100.0 and 100.7 to assign to devices because the 0 is the network ID and the 7 is the broadcast. You can't use .8 or .15. 8 is the network ID, 15 is the broadcast for the 8 network. Can't use 16 or 23 because 23 is the broadcast, 16 is the network ID. Okay, so let's look at next problem. Just a little bit. Okay, so this one, looking at some bigger numbers, but so you may, in order to get 512, but that is a power of 2, just extend the table by however many spots it needs to be extended to get however many bits you need for 512.
Is the subnet mask still just standard?
The subnet mask is gonna be whatever that /16 represents. Yeah, I didn't put it down because I'm wanting you to make sure that you understand that that /16 tells you what the subnet mask is. It's first 16 bits of the address or network IDs. So that tells you that the subnet mask first 16 bits are binary ones. Tell you what the number of the decimal number is. So another, take a few minutes to get this. And just because it's a bigger number, it doesn't make it harder really. You just have to, be able to double 128 and then double it again. So. Just back of it, I will extend the table. Can't draw a straight line though. There's the extra 2 columns that you would need in the table to get to 512.
So, thing is like.
Don't shout it out, just raise your hand if you've got the answer to new prefix. Yes,
25.
25, okay. Correct, and you got that by taking your,
Two to the 9.
looking at your table and seeing that you needed 9 bits to make 512 subnets. And you take that 9, add it to 16, which is the original prefix, and you get 25, right? And how about, I'll just write it down. Somebody else for the new subnet mask.
I'm wrong, 255, 255, 255, 128.
It's not wrong. Right. Okay. So, you know, since it's more than an octet, then 8, hopefully you know by now 8 bits makes 255. So that fills in your original subnet mask, and I'll just put it down here is for, so we have it in front of us. So that was our original subnet mask. So if we have 9 bits, well, 8 of them are going to fill up an entire octet. So that's where this 255 comes from. The third 255 is the first 8 bits of the 9. And then the 128 comes from just, you know,
Yeah, I get that.
right there.
Cool.
And then the rest of our 4th octet looks like this in our subnet mask, right?
Oh.
So that's what the 4th octet looks like. And the 1 in the 128's place means it's 128. And the rest of those are host bits. And so how many hosts per subnet do we have? 126. So 2 to the 7th gives us 128 minus the 2 is 126.
So when it's more, you just go all the way to the 120. Is that what you're saying?
Is that now?
When it's more than 2 to the 7th, you just go to the.
Yeah, I just keep extending the table.
I
yeah.
know that, but I'm saying,
Yeah.
you figure out the rest of it, you just know when you go down.
Yeah, I mean, it's not gonna be too often, but I mean, I think there was a problem in the Netacad that said 1,000 subnets, right? So you'd be going to 10 bits to get 1024 subnets.
That was the last problem.
So, okay, so I think for a lot of people, the thing to do when you're presented with a problem like this, where you're just told subnet for a particular number of subnets, is, you know, write the steps down. Find the power of 2, whatever the superscript is above the 2 that gives you that number. Okay, now if it's not, if they give you a non-even number, like if I gave you 500, you know, you just know that the 2 to the 8th is 256, that's not enough. So you have to go to the next power of 2. So you find the power of 2, or you find the value that represents the power of 2 that meets the requirement for the subnets. And whatever number that is, whatever the superscript is, that's your number of bits that you need to reallocate from the host portion to the network portion. That means just adding bits to the subnet mask. So that's how we get the prefix. We start with 16 bits. We add, in this case, 9 to get 512 subnets. We add 9 to get our /25. New subnet mask is you just take those 9 bits, put them in your table. Well, since our original is 255.255.0.0, we start in the third subnet. And since we filled it all up with the first 8 bits, we get a 255. Then we got to go into the next subnet or the next octet. And that gives us our 128 in that fourth octet. And then number of hosts, just count those zeros in the remaining zeros after you've come up with your new subnet mask. However many zeros are left at the end is raise that, 2 to whatever that is, you get your -2. You get your final number of hosts. I said, I wrote 26, I meant to write 126. Okay, so those are the steps. And then if you're asked to enumerate them, now this is the type of problem that's a little bit trickier in terms of enumerating the subnets, because we're dealing not in just a single octet. Our subnets will be in the third and fourth octet. So as always, our first is our original. Okay, so that's our first subnet. And again, when I say our original, it may not always end in a 0. For the problems that we see here, most likely it will end in a 0. But it could be in real life with that a ISP will give you, something like 10.16/28 or something like that. So they're not giving you the 0 because maybe that's already used by somebody somewhere. But for the most part, it's going to end in 0. But the process is the same. Whatever you're starting with, whatever the problem says, this is your starting point, that's what you put down as your first subnet, of course, with the new prefix. And then our next one, so 44.99. So what happens here? We did 0. What are we incrementing by? 128. So that's our next one. So that's our second subnet. Right? Because, our rightmost bit is in the 128 field.
Let's do increments.
So what about the next one? The next one, if you increment 128, increment by 128, you're going to get 256, right? And that's not a valid number, so you can't put 256 in that fourth octet.
So we put 1.
So what do?
Go up 1.
1.0.
Huh.
So because,
Would it be 255?
This is 256, gotcha.
1.255?
Okay.
yeah, if you look at this, I'm not sure if this might be more confusing to people than helpful, but if you look at this, we're working in base 256 for each octet, or for the whole IP address as a whole. So just to give you an example, when you are counting and you get to 99, what do? You add 1 and you carry the 1 from this 9 to this 9, and then you carry it again and you end up with 100, right? Or, same thing, when you're at 9 and you add 1, you carry the 1. and you get to 10. Well, you're doing the same thing here. You're going from 128, you're adding 128, which brings it into the next place value. In the next place value here just happens to be values that go from 0 to 255. Okay, so we're into the next place value, and we do the same thing. We add 128 to 128. Since 256 is sort of like 10, we put the 0 down, carry the 1, and we get 1.0. And then we just do the same thing. We add 128 to get the next one. So what's our next subnet?
Dot 1.128.
Exactly.
2.0.
2.0.
And then 2 points. Yeah, see, now you can see a pattern, right? And you don't even really have to think about it anymore. It's going to be 2.0, 2.128. 3.0, 3.128, on and on and on and on, until the last one will be 255.128. Last subnet here will be 44.99.255.128. And that's why I say the last subnet, the value, in the octets that you're doing the subnetting in this case, the third and fourth, the last subnet, those octets will look like the last octets of the subnet mask. When we're dealing with only the fourth octet, like in the last problem, our last subnet was 248, and that was the value of the fourth octet of the subnet mask. So that's, so if you, like if somebody asks you, what's the last subnet here? Well, basically you're counting by ones in the third octet because the entire octet is part of the network ID. So it's just 0, 1, 2, 3, 4. And so the highest value there is 255, and the highest value you can go in the fourth octet, since we're only the one, this leftmost bit is part of the network ID, the highest value we can go is 128. But again, I wouldn't even, do the mental gymnastics, just look at, we added, we changed the third and fourth octet. And so our last subnet is gonna reflect that. It's gonna look like, just like the third and fourth octet of the subnet mask. Okay. All right, so the last step that you may have to do is is enumerating these. Well, these are enumerated, but finding out the host values for each of these. So for the very first subnet, move it up in a second. So what is the first host address? 1. And the last host address.
126.
What's that?
127. 126.
Yeah. It'll always, just so you know, the last host address will always be an even number, because if you go one more, it's an odd number. That means the 1 bit is on, which means it's a broadcast. Okay. So whoops, sorry. If I do that and I don't correct myself, make sure you correct me, because sometimes my fingers don't do what my brain commands. Okay, and then the next one.
129.
44.99. 44.99.129, right? You just, sorry, 0.129 through 44.99.0.
One,
254.
oh, 254.
Because So it basically, remember what we said about you go to the next subnet and subtract 1 to get the broadcast address for the previous subnet. So if we subtract 1 from this, we get 0.255.
Which you can't have because it's broadcast.
Right.
So you have.
It's like you're subtracting 1 from 100, that leftmost 1 goes away and you end up with 99. Well, here, this goes away and you end up with 0.255 for the broadcast, and then 1 less is 254 for the.
You're just based on usable networks. Anyway, right?
Usable networks.
Like, because you can't have the 256 or the 255, so it's like -2 from that, so it's.
Usable host addresses, yeah.
Yeah, that's what.
So whenever we say host addresses, that implies that you have to be able to assign an IP address. Okay, assignable IP addresses to an interface is what host addresses mean. So, right, you can't assign the network ID, the .128, and you can't assign the broadcast, which would be 255. And so now you've got your pattern. It's going to be 1.4499.1.1 through 44.99.1.126. And then 44.99.1.129 through 44.99. Yeah. 254, yeah. So I'll just put those down just to complete the pattern. And so, since always check your work, to make sure that you didn't somehow, start enumerating all these and you made some sort of mistake when you started putting down the host ranges. Make sure that it jibes with what you came out with for host per subnet. There's the 7 bits, so 128 minus 226. So just make sure 1 to 126, that's 126. 129 to 254, you'll see it, that's also 126. So just make sure you verify before you do too much writing, if a problem ever requires you to do that. Not too many, you won't really have to do that in problems. Most of, like in a certification test, it's multiple choice. You don't sit there and write down big tables or anything like that. But you may be asked for, like, what is the last host address of the 3rd subnet, given this particular problem. So you'll need to know that it's going to be, that's the last host address, or it was the broadcast address, or whatever else. Okay, is it starting to make sense, I hope? Now, we can't do, that many sample problems, examples, just time-wise, because we have to move on to the next topic. So there are some worksheets in Canvas. I'll show you some of them before we leave, I think, if I remember. If I don't, you can remind me. But anyway, there's some problems in there. They're kind of like word problems, which I know everybody tends to hate. I don't like them. I like it, more straightforward like this. Just ask me the question. But they're the same type of problem as this. And I think, I can't remember if the answer sheets, if the answer is already in there. I'll look before we leave. If they're not already in there, then I think I have answer sheets and I'll post those as well. So that way you can check your work. Okay, so I'm gonna go on, well, not really, not quite to the next subject, which is VLSM. Got another subnetting problem. Yeah, subnetting 3. Okay, and again, it shrinks everything up for some reason. Is that big enough for everyone to see? Okay, same stuff, same problem, for the most part. But what's different here is, well, first off, I should have asked, how many subnets do we need? So we'll just kind of work through this one together. How many subnets do we need to accommodate this network? Imagine this is a a headquarters, WAN going to another city. And in the branch office, you have 60 hosts, so 100 hosts in the headquarters, 60 in the branch office. So how many, not hosts, how many subnets do we need for this little network here?
63.
3, right? There's 3 networks. Well, I remember Zoom people. So here's the first network.
Right.
Here's the second network. Where's the third network?
Flash through the router.
Right.
Sorry. Oh, good. It fixed my oval. So there's the 3 networks. And so we got to accommodate 3 networks. So we need 3 subnets. Now, 3 isn't a power of 2, so we just have to come up with the next closest. And so I should have asked what the new prefix will be, but we'll do that. So what is the new prefix?
26.
26, right? We need 2 bits to accommodate 3 subnets because 1 bit isn't enough. 1 bit only gives us 2 subnets, so we need 2 bits to get us to 4. And so if we put our little ones in our table, should give us an idea what our new subnet mask is.
You're right.
So new subnet mask is going to be 255.255. Whoops. 255 dot what?
What is that? 692?
192. Yeah. Okay. So let me just put here real quick.
/26.
All right, so let's just enumerate our subnets. Our first subnet is going to be 110.19.23.0. And our next one will be 10.19.23.64. And our next one,
Really quick, I got lost of things. So we need 3 subnets and we are doing 2 subnets and stuff, or is it?
No, it's to the power of 2.
the 2 bits. Remember, 2 bits gives you 2 squared or 4 subnets. Just think of it like this. If you have 2 bits, well, let me ask you this. In the decimal system, if you have two digits, 2 place values, how many values can you create? What are the total number of values that you can create with 2 digits? 2 digits.
99.
Well, those are the 99 is the highest value, but you got to remember 0, right? So 100 different numbers, right, with 2 digits. Well, with 2 binary digits, what are the possible values of 2 digits in binary? 0, 0, 0, 1, 1, 0, 1, 1. And so when we create our subnets, we're going to use that fact. Our first subnet is going to be these 2 network ID bits being 0, 0. That gives us this. Our next one is going to take these 2 subnet bits being 0, 1. That's the 64, right? Because the one is in 64. And then the next one is going to be 1, 0, which will be our third one, which will be .128. Started doing it. Spans out. And then our fourth subnet is going to be with both bits being 1, 1, being ones, I should say.
192.
Which is 192. Again, our last subnet is going to reflect the value of the subnet mask octet that we messed with, which is the 4th octet here, 192. Okay, so yeah.
How do you accommodate the 100 hosts for the one network if you can only have 62 in one
I
subnet?
was waiting for somebody to catch that.
I was, yeah.
All right, so here we have a problem. How many purposely didn't ask how many hosts do we need or how many hosts do we get? Because I wanted somebody to recognize that. How many hosts per subnet do we have with this?
64.
2 to the 6,
62, yeah.
62. Well, that 100 is a problem, isn't it? So basically, this is an undoable problem. You can't do it with traditional subnetting as we've been doing it, where all the subnets get the same subnet.
That's why we're gonna do the
So this is the whole reason for variable length subnet masking. We've got 254 addresses. We only have 162 host addresses we need. Why the hell can't we make it work? Well, the reason is because if we just split, take our 4 subnets, well, with 4 subnets, they're divided in 4s. That 254 addresses is essentially divided by 4 to give you around 62 hosts per subnet. So, yeah, so what do? What we do is VLSM it. So instead of looking at this problem from how many subnets do we need? Like, first off, if you were looking at a problem, if you were the network engineer and you had to solve some sort of problem like this, first thing to do is, well, count up how many hosts and do you actually even have enough address space, period, right? Because if there was more than 254, then there's no way in heck you're going to do it. Really, if there was more than, because you got to subtract the network and broadcast for each subnet, so that's 4 more addresses gone. So if it's more than 250, there's no way in heck you could do it. But in this case, there's only 162 addresses that we need. So I bet there's a way to do it. And so here's where you don't consider the number of subnets. You look first at which network what's the most hosts that we need on any one network. In this case, it's going to be 100, right? So basically, we solve the problem based on that. We say, that, okay, let's take our initial network and what subnet mask or let's look at another way. This is where you start just looking at the prefix. All right. Say what prefix gives us enough host bits to accommodate 100 hosts.
You can go up one. There you
Yeah. 20,
27.
25, no, 20, well, no, 27 would reduce our host bits down to 5. So no, we need one more. Right now, we have 6 host bits with a 26 prefix, right?
Oh, okay.
We need 7 bits because,
Yeah, 'cause that's,
so what prefix value would allow us to have 7 bits? 25.
oh, 12. That's what's up, I'm thinking, right? 2 to 7, 120.
So 25. So that's just 1 bit. So we're basically right here. Oops. We're basically right here in a 4th octet for this, our subnet map. Whoops. Jeez. Right there. So this is what /25 looks like. Okay, so when we do /25, how many subnets do we get? 2, right? When we do a /24 to /25, we get 2 subnets.
Right.
Because it's only 1 bit, right? So what are those 2? Here, I'm gonna erase these. What are those 2 subnets? The .01, 110.19.23.0, that is always your first one. What's our second one when we do a /25? 28, exactly. I'm gonna put the slash number down here because now it's important to see it because it's gonna be different. Okay, so that 128, well, here's the way I like to do it. We first subnet for the maximum number of hosts, which in this case, 1 bit, because we need 7 host bits. So that's the other way to do it. Well, how many hosts we need? Just start writing zeros down, starting from the right. And then once you have enough zeros, in this case 7, to get 100 hosts, then you put a 1, and then you say, okay, only 1 bit is being reallocated. And now we are going to go and assign this network over here. So this guy's used, we can't use him anymore. Now we've got this guy. Well, this guy has 128 addresses, 126. We only need 60 for the next network. And we need a 3rd network. So let's just,
You can split that.
break this up. What can we do? How many bits do we need to reallocate from this? You know, right here, how many bits do we need to reallocate to give us 2 networks? Because we need 2 more networks, not just the 1. Yeah, one bit, right? So we now just say, all right, 1, 1. And what does that make this?
26.
26.
26.
Huh.
Okay, so when you do a /26, we know that there's gonna be 2 networks. And what are we counting by?
64.
We're counting by 64. So basically just add that 64 to your 128 to get your next subnet.
Oh, wait.
Dot 192/6. Okay, so now we've got these 2 subnets and this first one up there, the .128, has 62 addresses. So it'll work here. So let's put it over here. This is what we have left. Well, we only have 1 more subnet. And we could say we're done with this problem. And, you know, if that's all the problem required is that you subnet appropriately to meet the requirements, then you are done. You know, you'd assign the .192/26 to our WAN network. The thing is that might be a waste. You know, you might expand later on, have a branch office with 30 hosts, right? So probably the best way to do this is to say, well, how many addresses does our
The last one.
well, let's actually not go there yet. Let's just say we want to at least create, for expansion, another subnet that'll accommodate, won't be 60 hosts, but let's say 30 hosts. So to do that, you can just add one more bit. Yeah, just subnet it one more time by adding one more bit. And now for this third subnet, it's going to look like .224 in the subnet mask. And now again, we just made two more networks by reallocating just one more bit. Oh yeah, and we're counting by 32, so it's gonna be 224.
Right.
Slash.
/27.
So those are the two networks that we create by reallocating one more bit from the 192/26, make it /27. So we've got a 30 host network here, and we've got a 30 host network there. What most, what Cisco would want you to do is what subnet mask will give you two IP addresses?
/30,
What prefix? Sorry?
30.
30, yes. So a /30 will give you two IP addresses. So what we can do is we'll reserve that top one for 30 hosts for some future LAN somewhere. We'll make that a 30, and now we've got 8 little WAN networks. We may not need that many. We could probably, do this some more and, make it /28 and whatnot. But for right now, we'll just do it like this. And then you can basically say, well, if we enumerate these, there's 8 networks created between a /27 and a /30 because it's 3 more bits, right? 1. Now we're there, a .252. So this is going to be .2. Oh, and we're counting by 4s, by the way. So 228, .232, .236. Counting by 4s, it's all we got to do. .240, .248. I'm sorry, 244, .248. And then our last one will be .252. Okay, so that's our very last subnet. It's going to look like 110.19.23.252/30. All these are /30s. Again, you wouldn't necessarily, for this situation, you may not need 8 WAN subnets, but I didn't want to, do it again. But you could have done a /28 with this to make a 16 host or 14 host network, and then just you have 4 WAN networks left. So I just decided to, end it here. So one of the problems that you're going to see in your skills exam and stuff, it's going to say use the last possible /30 subnet for the WAN links. Or there might be 3 WAN links, and it'll say use the last one for the Prescott to Verde campus WAN link. Use the second to last one. So you'll basically use that one for that's the last WAN link, or the last WAN subnet /30. That's the second to last, and that's the third to last, 244. So, and then what are the addresses? What are the possible addresses here that, if you need to sign, because you're going to need to assign addresses to those router interfaces. .25 what? What's the first possible address here? 3. Just add 1.
3.
And then .25 what?
4.
Because 255 is the broadcast. Just 2 addresses, 253 and 254. The 248 gets 249 and 250. 244 gets 245 and 246, and so forth. So that's, that's basically what is kind of expected of a network person that's doing subnetting that involves wide area network links that are point to point when you only need 2 addresses, the best way to conserve is just come and take, you know, the last subnet of, you know, where you don't need any hosts anymore. So I could have gone one more time with a /28 and done .224 and .240 and just used, you know, 40, 44, 48, and 52 or something like that. But they're gonna expect that you're just gonna subnet with a /30 for your WAN links. And in my problem, like in my skills exam, I say, use the last /30 for this link, use the second to last for this link, and so forth. All right, so that's why you need the VLSM, is because, yeah, you may have enough addresses, but if you just do traditional subnetting where every subnet gets the same subnet mask, the problem may not be solvable, like in this case. So let's take a break, and we've got another VLSM problem to do. I'll put it up on the board, and whenever you feel like it, you can start working on it. And you know, hopefully it'll make sense to you, or at least start to make sense.
There's 3 this time. Okay.
Yeah, this one is reasonably straightforward. There's only 2 different subnet masks that are needed. You still have to feel this.
It's really. Yeah, I use a series, and like I spent so much time on it for 6, and I got some value out of it, but like.
I'm actually going to delete that because it really doesn't apply. That still applies.
So you're. Yeah, like so.
So for the block size, is it the last number of the network ID Or is it the last number of the? So would it be the first zero or the last one that you count by? So would it be 64 or 32? For the block size?
64,
So it's the last one in
the last
okay.
one.
Okay,
Yes.
cool, thank you.
So how long would break? I figured quarter till.
Is this the beginning of this rabbit hole? Like,
No, this
we
is,
have- we absolutely have to nail this before we can get to anything next.
no, plenty of people go through all four, well, three classes. Go through the whole, even get CCNA certified without really getting it nailed.
Oh,
Like I think that, like I said, you can pass the CCNA if you basically have to guess on all the subnetting related questions. Because you still might get you still might get one or so right, but you better know everything else because there's enough subnetting questions, related questions that if you get them all wrong, then you're going to be pretty close to, failing the test. You have to get somewhere. I mean, they don't tell you exactly, like there isn't a strict percentage, it's based on number of points. But it's somewhere close to 80% that you have to get to pass the CCNA. And so if you at least, one of the things that that I find that if you can't, even if you can't do everything that we're doing here with subnetting, if you can look at the address of a host along with the subnet mask and look at the default gateway that has been assigned to that host and know that and tell whether that default gateway is in the same network as the host, because it has to be for it to work, then that, there's actually, last time I took, there's a couple at least problems related to that. So if you had like a host with an IP address of, let's just say 100.33, and it was a /27. Okay, if that's your host address and you look in the configuration and its default gateway is 66.
How do we find the default gateway?
Well, like if it was a PC, there's simulations in the CCNA. So in the simulations, if it's a simulation question, it might just be in a diagram where it'll, have the network topology and it'll say host and give you its IP address and subnet mask, right? Or IP address and prefix. And then it'll also list what its default gateway is. Or it'll just show the router in the diagram and have its IP address there, okay? So if that's, in this particular instance, if you have this, then is that going to work? You have to, is that appropriate? If that was the default gateway, is this a valid host address for that default gateway, or turning it around, is that a valid default gateway address for that host? Well, with the /27, okay, that you're here, right? 111. And so that means that the size of each subnet is 32 long. And that means that this guy's in the 32 subnet and the next subnet starts at 64. And the first host address would be 65. So this guy's in the next subnet. So you can't have that. This wouldn't work. He couldn't communicate with him because if he's the default gateway, because he's in a separate subnet.
But you said it's 32 network, right? That's 33.
No, that's actually the IP address of the host. But he's in the 32 network, right? This is the first address in the 32 network. And this is the second address in the 64 network. So there are two separate subnets that's an invalid configuration.
Could you explain real quick, how to check that the CIDR, that, is it, so /27, is that what it is? They just have to be /27 since 32 bits, or /26 is 64, so each address, let's say /26, will have to be each address, no more than 64 number, is that?
Well, okay, so if you see that /27, then you know that the last octet of his subnet mask looks like this, right? Because the first three octets are going to be 255, 255, 255, because that's 24 bits. And then the last octet of the subnet mask is going to be 111 or 224. So based on that, you know that since you always look at that rightmost bit of the subnet mask, and that's the increment that your subnets are going by. They're going by 32s. So if the subnets are going by 32s, then you can surmise the first subnet with this 1011 address was 10110. The next one was 101132. The next one was 101164, 96, and so forth. So that tells you that this guy's in the 32 subnet because it's 33. It has to be between 32 and 64. And since the next one is 64, that tells you that this guy's in the 64 subnet, which means they're in two different subnets, which that wouldn't be a valid configuration if this is the default gateway for this host, because you can't communicate with another device in another subnet unless you go through the default gateway. And if that's your default gateway, you're out of luck.
But that wasn't the default gateway, otherwise that would work. Would that-
Was that, if this guy was,
Not the default gateway, that
if he was
another-
62, then he's in the same they're in the same network. Because 33 is in 32 network, the next network is 64, so 62 is in, these guys are in the same network now. So that would be a valid configuration. And again, you know, like I said, the computer goes and does a binary AND on the subnet mask along with the IP address. So when you binary AND 100.1.1.33 with that subnet mask 255, 255, 255. The fourth octet of that subnet mask is going to be 224. So if you binary AND those, well, anything ANDed with 255 is just going to be the original number. So no, it's going to be 100.1.1. Then we just have to binary AND 33 with 224. Well, 33 looks like 0, 0, 1, 0, 3, 6, that. And 224 looks like 1, 1, 1. So if you binary AND those, you end up with 0, 0, 1, 0, 0, 0, 0, which if you plug that into this table, 0, 0, 0, you get 32, okay? So that's how the computer knows what network it's in. It does the binary and with the IP address and the subnet mask, and what falls out is the network ID. Okay, so if you do that binary and, then whenever the computer needs to talk to the default gateway, which originally I had as 100.1.1.66, it does the same binary and 255, 255, 255, 224, and you end up with 100. And then if you binary and 66 with 224, you're going to end up with 0, 1, 0, 5, 6, 8, 224. You end up with 0, 1, 0. Well, 0, 1, 0, 0 is 0, 1, 0, 0. That's 64. So by doing that, you came up with the computer's network is 100.1.1.32. The default gateway, you applied the same subnet mask, is 100.1.1.64. Separate subnets, separate networks. So that wouldn't work as a configuration because you can't talk to a default gateway if he's in a separate subnet. So that's, behind the scenes, that's what the computer does, is it does that binary and to find out if the device that it's trying to communicate with is in the same network or a different network. Okay, let me erase all this and let's do this problem. Whoop.
Just want to say you have the patience with Saint. Appreciate it.
No problem. I've done this a long time and it takes patience. People learn at different speeds and frankly, I'll be honest, some people don't learn at all. They just, but they still go on and can be very, good at IT. It's not a skill that exempts, if you don't get it, eliminates you from doing a job in this field. It might prevent you from getting, CCNA if you can't get everything else right, if you get most of the subnetting wrong, but, you can still do plenty of things without a CCNA. Okay, so let's look at first off, how many networks are there in this problem? 6 networks, right? So, right?
2, 3, yeah, 6.
Let me just circle them, make sure everyone sees that. Trying to circle them.
And you drew a perfect one right there.
Yeah, there's the LANs and then here's the WANs. So 6. So we have 6 networks. So since right off the bat, hopefully you may have looked at this and said, well, there's 3 networks of 60 hosts each. And if I, subnet this to accommodate 60 hosts, that means 2 bits, right? Because I need 6 host bits. And so I'm not really even going to look at how many networks because this is a VLSM problem. So I need 6 host bits. So to get 62 host addresses. So that gives me a new prefix and subnet mask that accommodates the max host per subnet. It's all the same. The new prefix is what?
26.
46, right? I just wrote down the 2 ones there. And then the new subnet mask is gonna be 255. 255. 255. What?
92.
Okay, so let's just, let's start enumerating the subnets because that's what you have to do to make sure that, you can accommodate, that you allocate the addresses properly. So 215.1.1.0/26 is our first subnet. And by doing the /26, we make how many subnets? How many are we gonna have? How many subnets? 4, because 2 bits. 2 bits, we're gonna have 4 of them. So let's just start enumerating the others. Got what? It's our second subnet.
64.
64. Okay. And our third.
28.
And our final one that /26 gives us is 192.
Or 192, sorry.
If you write the subnet mask down, like I did, then when you're enumerating your subnets, if that, wherever you're working, whichever octets you're working in this case, the 4th, that doesn't match the octet that you changed in the subnet mask, then, you did something wrong, you added wrong or something. Okay, so there's our 4 subnets. Well, we can just start assigning these. We can put this one here, and this one here, and this one up here. And we've got 1 left and 3 networks. So, what do we do? What's
Subnet,
subnet the subnet? Exactly.
subnet section.
So what would you do with, you've got a /26, you need 3 more networks. But you want to conserve IP addresses because your network could grow and you might need more lands. You're not going to get any more 60 host lands, but you might get some smaller ones. So what would you do with this?
33/30s, right?
Yeah, so /30 is where we ultimately want to go. But like if you were doing this and you were like, okay, I'm gonna do my spreadsheet of my subnets and I'll just have that there so that if we do expand and we need more lands that have more hosts, they're gonna have addition, something up to what we can accommodate host wise, then I want to have those at the ready. Right now, all I need is 3 /30s, right? And so you could basically say, well, let's make the biggest lands that we can at first and reserve those. And so if we just add a bit, then we get 2 networks out of that. What was what, 64, 192, right? And so if we add a bit, we're now at /27, so we're here. So from 192, our next one will be 224. Okay, so we've got that. And we could then say, well, might as well do that one more time. And, this will give us a 30 host network. Let's do this one more time, make that a /28, which would look like this. And so now the two networks that we make are going to be the 224 and the 240.
240.
Mhm. /28. Okay. So now we've got that. And so we could right now, since we need 3/30s, probably turn that, because if we add more lands, chances are they might be like in different cities, so we're gonna need more WANs. So let's just make our WANs out of this 240/30. So we went from a /28. So these two banks of addresses, we can, put as reserved for the next expansion. This is what we can use to assign those WANs. So we've got the 240, and I'll just write them here. We've got the 240 and the 244 and the 248 and the .252. Oops.
42, right?
And .252.
Put it in that show.
So here's our four WANs that WAN subnets that each have two addresses, the .240, the 244, 248. So if I, again, in real life, you could, assign whichever of these four that you want to the three that are there. If you have a problem like a packet tracer problem where you need to assign exactly how I specify in order for it to grade right, I would say put the 252 subnet over here. So you might. .252 subnet is there. So put that there, and I might say, and I wouldn't say the 252, I'd say the last /30. And that I might say the second to last goes, and I would name the links in the problem so you'd know what I'm referring to. The
So-
248
So
goes
for
there.
This one, the first two are gonna just not be used and be available. and
Yeah, they'll
we're
be
using
available
only
for
the last
expansion.
one to assign to the WANs.
Yeah.
Okay.
So now we've got one WAN left, the .240 for future expansion. And we have, a two rather small subnets. And those could be potentially, no, actually you couldn't combine them. Yeah. So you couldn't combine those. You'd have to have, two separate subnets on your network, /27 or /28. But in any case, this takes care of the problem. You got all of your LANs addressed, and you've got all your WANs addressed, and you've got one WAN left over and two small LANs left over. Okay, and then if you expand and you needed more than a /27 or /28, you just have to go back. If these were public addresses, you'd go back to your ISP and say, I need more addresses. That's what you'd have to do. But hopefully, when you first worked with your ISP, you kind of planned for expansion. But if not, you just go back to them and say, I need more. And they charge you for that. So they're happy to get your business as long as they have addresses. That's the other thing. That's why, IPv6, because all the IPv4 addresses have been doled out to internet providers. Now, they haven't used all of them necessarily. They probably, the big ISPs that run the backbone of the internet probably still have banks of, some class Bs and Cs left. I think there's no class As left, but, so you can still get IPv4 addresses that are public, but, they're becoming scarce. And that's why IPv6 eventually may be, forced upon us. If, doing NAT and all that stuff just isn't cutting it anymore. Okay, so that, hope that made a fair amount of sense. Now, this is one where the largest number of hosts happen to be the same on each network. So all of these LANs got the same subnet mask. And then a problem like this, example 2, where you've got, make this a little bigger. So now we have kind of the same situation with the 3 WANs, but the different LANs have different numbers of hosts. So with this problem, you do it the same way. You want to know how many LANs do you have, how many WANs do you have, but your total number of networks is going to be 1, 2, 3, 4, plus the WAN is 7. WANs is 7. And then you just start by subnetting and accommodating the most hosts, 125. So I never put an initial network out here. That would help. So I need to tell you what the initial network is. It's going to be a /24 because if we're like a /16, then you wouldn't need the PLSM. But with /24, I'm sure you can do it with /20, 125, 185, 213, 225, 225 plus 6, 231 addresses are going to be used. So I think we can do it. So I'll just put a 149.0.1.0/ is our starting point. So we just need to basically accommodate the largest number of hosts, and then the second largest number of hosts, and then the third largest until and then, in this case, it's going to basically be 1, 2, 3, 4 different subnet masks for the LANs and a /30 for all the WANs. So come up with the appropriate, but I would just do it like I did. Don't worry about the subnet mask too much. Just put your bits down when you subnet the first time. Let's say what that first subnet is going to look like. What's the first prefix value we're going to come up with to accommodate 125 hosts? What's that first prefix? I think I heard it, but
25.
25, right? Because 125 hosts, we need 7 bits. So 7 bits means that we can only have 1 bit that's reallocated. And so 1 bit gives us 2 networks. So just write down, that's the first network. And you could assign that, to the 125 hosts. But what's the second network? What's the second /25 that's created? 149.0.1.0 is the first one. 149.0.1 what? 128, right? So .128/25 is the second one. That's all you've got, right? That's all you create. So now you're gonna have to subnet that /25. And just keep going down that way until you've taken care of all 4 of them. I'll give you a few minutes to do that and then we'll do it together. And I think I'm gonna have to, start getting into module 6. Or, yeah, 12. Module 12. IPv6.
Fair enough.
And for those that, still need to go over subnetting, whatever aspect of it. There's open lab on this Saturday. Brendan is probably better if Brendan and Alan are here. Alan's got it, but has a hard time explaining it. So Brendan's better at explaining it, is what I'm saying. I might try to be here Saturday, but I can't guarantee it to help out. So, and then, if you come before class, I'm gonna try next week, it's only one day, to be here a little bit, an hour early. So if you come in and need to try to go over things just one-on-one, come in at 4:30 or something and see if we can next Monday. Yeah, maybe. Yeah.
Oh, wait, no. What about the Monday after that?
So next Monday is the Thanksgiving week, so we only have next Monday. Monday after that, well, I don't know, I haven't thought that far ahead. I'll be here, but yeah, I'll probably be here ahead of time,
Next Monday, I'm gonna be not here, but
Okay, the following Monday.
Are we doing in-class labs next Monday or?
We're gonna do the 11 and 12 labs on next Monday.
but you can bet a Monday I will be here.
And possibly if the labs go smoothly for, the first group that does them, I can be doing subnetting problems for people that are waiting. And since everyone's kind of had their shot at first go, I'm just gonna make it first come, first serve this time. For the, first 10 that go up to the bench.
This is tonight.
And on Monday. On Monday, I think on Monday, that's all we'll do. So Zoom people, next Monday, we're only gonna be doing lab, module 11 and 12 labs. There's only 2 of them, but they might take a while. Shouldn't be too long, but so there's no reason to zoom in. I know that Anthony came last time. If you wanted to come again, if you're still here, you could. Yeah, Anthony. Actually, anybody can. It's just, if all of you show up and everybody here shows up, it gets, we may have to do it in 3 shifts, which could be problematic in getting it done. I really recommend that if you, depending on how many you still have yet to do, come in this Saturday, so you're not trying to do 3 chapters, 4 chapters on the final weekend or the final 2 weekends, whatever it's gonna be. What do we have after this? Look at the calendar. So we've got this weekend, the next weekend we won't be here. And then we have the weekend of the 2nd. Is classes done on the 7th, I think, is that right?
I thought.
Because this is week 6. Yeah, class is done, well, the end of that week, the 8th, yeah. So really, there's only one more weekend before class is after this coming. There's only one more week, one more open lab, which will be the 2nd. Saturday the 2nd. Okay, let's go ahead and do this so that we're not here too awful late. What is the second network with the /25 is 0.1. What? 128. Okay. So now that we've got that, we can basically say, well, let's use this one, put this one over here for the 125 hosts. So that one's no longer available. Now we've got this one that's got 126 host addresses, and that's more than we need, thankfully, because we've got, 3 more to do, 3 more lands. So how many bits do we need for 60 hosts? How many host bits do we need? Well, I mean, no, how many host bits? How many
6.
zeros?
6.
So basically, our new prefix is going to look like that in binary, which means a /26. Okay, so we one more bit. We reallocated one more bit, so that gives us 2 networks. The second network that we've got after the 128 is 149 0.1. So what are we counting by? That's that bit that we just added is in the 64 column. So we're counting by 64s for this next subnet. So it gives us up to 192. Let me put the prefix in there. All right. So that gives us 2 /26s, and that will accommodate 62 hosts. So let's take the first one and give it over to the 60 host network. We've got 1 /26 left, but yet 2 subnets left. So we need to accommodate 28 hosts. So how many bits do we need for that? Well, how many host bits?
3.
For 28, 2 to the,
Oh, wait, no.
Oh, wait, sorry. No,
Uh,
fifth.
we need 5, right? So 5 host bits, which means one more, we can add one more subnet bit. So going from a /26 to a /27, again, gives us 2, doubles our networks, or gives us 2 networks. And we're counting those networks now by 32.
So that goes up to 224.
So our next subnet is 224/27. So these are the 2 subnets that we created by going from a /26 to a /27, the 192 and the 224. And it gives us 32 hosts or 30 hosts, and that'll accommodate this guy. So we have 1 LAN left, and we need how many bits for 12 hosts?
4.
4. So that means we can add one more network bit. Subnet bit, however you want to look at it, subnet mask bit, prefix bits. And that makes that a /28. And then we know that since we just we increased it by one additional bit, that means we're going to get 2 total networks. And that gives us 128, and we're counting by 16s now.
240.
144. Is that right?
240.
I'm sorry, what was
224.
128? It was 2.
That'd be 240.
It
It
was
was
192.
224.
So it's
Yeah,
240.
240. You're right. Sorry. /20. Okay. All right. Well, this guy we can assign to our 12 hosts LAN, and we have this guy left for our 3 LANs. So we know we have to borrow 2 bits or reallocate 2 bits because we need 3, and 1 bit won't be enough. So that goes to a what?
30.
30, which is just what we want for our WANs. So now we get 240 and 244 and 288.
Slowly starts shutting down.
So we can just, however we want to do it, 252 there, 248 there, 244 there. And we got that guy. And that's all we have left is a WAN, which isn't going to do us much good. It's not very useful to have a WAN network when there's no more addresses for your LANs, unless you get another bank of addresses, which, you could do that and still use this for your point-to-point links, and then whatever bank of addresses you get from your ISP, you would use for your LANs. That's what's left, and yeah.
So that's what
takes
you
care.
would do is, if you run out of hosts with these IPs, you would just get another, you would just pull from the bank.
You'd have to go, like, if there were public addresses like this, you'd have to go to your ISP and say, I need another whatever. Like they probably wouldn't give you a /24 because you probably don't need another 254. They might give you, let's say you say, I need another 60 addresses. They'd give you a /26. You do whatever you want with them.
Okay.
Did it matter that we left that one aside? Could we have used the 241 and left another one aside?
Yep. It's the only reason I did it where I pulled from the last is because I know that the instructions in the skills exercises and skills exam say use the last, 3/30s, like assign the last or say assign the last WAN subnet to, router A to router C, and the second to last to router B to C, and the third to last to A and between A and B. But in practice, it doesn't matter. You could use whichever one you want. It's just that, you're going to be following.
Telling you specifically which one.
I tell you which one to use for which link because, packet tracer, it's very, if you don't put exact, even though you might do it right, it might work the way you do it. If you don't do it the way I specify, then the auto grading of packet tracer says it's wrong, even though it would quote work. So part of it is just following the directions. There's no reason I had to use the first one for, well, I did. I didn't have to use the first one for the 125. I could have used the second one because that was also a /25, and I could have just divvied up that first /25 into the smaller subsets. But traditionally, and just working it out on paper, it works better if you take your very first subnet and assign that to the largest number of hosts, and then just keep going down from there. But it's not something you have to do it that way. It's just easier, I think. Okay, so I hope at least that some of this, set in and made sense. I'll try to post some more VLSM related examples, like for you to do just on your own. I might have a document or two that's got a couple that are different from these, so I'll try to find those and post them in the week 6 module, just so you have other stuff to do. In the meantime, let's look at IPv6. I don't think, let me just go back into module 11, make sure that I didn't skip anything that might have been at the end. Because the last couple of slides were dedicated, I thought, to VLSM. I didn't go over them just because I think it's more useful to do practice problems. And honestly, they throw a lot of tables in these, which some might be good for some people. I don't like to look at a whole bunch of numbers, and that tends to confuse me more than anything. All right, so VLSM was the last topic. See if there was another topic. Yeah, well, actually, the structured design, I actually skipped those anyway. It's just basically telling you, how to make sure that you reserve addresses, that you don't design it too close to what your current needs are, because you might have expansion. But that was about it. There was like one slide related to that. I don't really have anything to add, so. Okay, IPv6. Huh? All right, so 128 bits written in hex. So they all, big, ugly looking addresses that can be made to look a little bit less ugly by some shorthand that we'll look at. I think, that was covered in CNT101. We'll just do a quick review of it. But so they refer to each of these fields separated by a colon as a hextet, 16 bits, basically. It says octet, 8-bit, dotted decimal IPv4, hextet, 16 bits, fields that are colon separated hex. Okay, so the preferred format. Okay, so the preferred format is that you actually have 4 hexadecimal numbers in each field. And that way, when everything lines up. But in reality, people just don't want to write that much. So a lot of shorthand can be used. You don't need leading zeros. So 01AB can be just 1AB, 09F0. So you don't need those leading zeros. Obviously, it only applies to leading zeros, not trailing. So you can't cut off the zeros after the A or after the F, because that changes the number. But just like in writing decimal numbers, no one puts leading zeros in front of a number, unless you, for some reason, want everything to line up in a spreadsheet or something. Okay, so I don't know, when they say preferred, I'm not really sure who prefers it. But this is just, you know, I guess when you see it like this, you know that that is a correctly represented IPv6 address. When you see, you know, all 8 fields with 4 hex digits in each field. But, you know, without deleting zeros, that means there's a whole lot less to write down. And now there's another additional shorthand, and that is whenever you've got a bunch of zeros that are, here, let me just annotate. When you've got a bunch of 0 fields in a row, those can be shorthanded with this double colon. Okay. So double colon represents 1 or more consecutive 0 hextets. Okay, now you can only use it once because, you know, what the computer, when it looks at this, it sees that there's 1, 2, 3, 4, 5 hextets that have values. So it knows by the double colon that what's in between the 1111 and the 200 are 3 sets of 0 fields. But if you had 2 double colons, it wouldn't know how many 0 fields to put where. So it can only be 1. Okay, and you know, you can be real cute with you know, your letters A, B, C, D, E, F, and make words and stuff like that. You know, so they put cafe in there. So, you know, you can play around with that a little bit. Why am I not? There we go. Oh, delete that. Whoops. Sorry, I hit the wrong darn key. Everyone just saw subnet and IPv6 address. Oh no. It's pretty easy. There's nothing to it really. Oh my gosh. Sorry, I just went to I should just start it over. I didn't realize I'm gonna have to back that much. Oh my, yeah, let me just start it over because that's IPv6 address types. That's where we're at. And let me delete the. All right, so unicast, multicast, and anycast. Unlike v4, you had unicast, multicast, and what's the third type in IPv? Broadcast. No such thing as a broadcast in v6. The multicast takes care of all the functions that v4 uses broadcast for. The anycast is a completely separate, it's not anything like a unicast or a multicast. It's a totally separate function that is available in IPv6. What an anycast does is it allows you to actually set duplicate IP addresses on 2 or more different devices. The most common thing would be a router. So let's say you have a big network and you've got a whole lot of host traffic going out your LAN to get out to the internet and to other networks. Well, that router might get overwhelmed. So you could add another router to the same LAN and give them the same address. You'd have to specify in the router configuration that it's an anycast address. That way the router knows, oh, there's at least one other router that has the same address. And basically the routers then work with each other to determine who should take the traffic by using what's called redirects. So if one router is, if between the 2 routers, they say, okay, this router should have the highest priority. If a device sends to the secondary router, you can send them a ICMPv6 redirect and say, use this gateway instead. That's all an Anycast is. It's just a address that can be assigned to multiple interfaces on the same network when you need to, let's say, load share, load balance. Okay, so we don't really, it's kind of a weird thing. We don't deal with it at all in this class. So that's pretty much all you need to know about Anycast. Okay, so the IPv6, the prefix, there's no such thing as a subnet mask, as you know. The prefix length is, for the most part, for host addresses, it should always be 64. So that makes it really easy. You don't need to be having /23s and 26s, and it's just the first 64 bits is the network ID. The last 64 bits is the interface or host address. Okay, so it can, be from 0 to 128, but for LANs and for assigning to hosts, 64 is the standard, and that's what should be used. Because if you start doing other things, it's going to be, you're making life hard on yourself. You'll see different prefix numbers, but that's to represent something else. Like I said, with IPv4, an ISP might give you a /18 or something like that. And you can do whatever you want with the remaining 14 bits. You can subnet, make big networks, small networks, or whatever. It's the same thing with IPv6. ISPs are most likely to give you a /48. In other words, they'll give you the first 48 bits of your IPv6 address, your public IPv6 address. You have the next 16 bits to do whatever you want. In other words, that's your subnetting part of your IPv6 address. And then the last 64 bits are always going to be the interface. So that never changes. Unlike v4, where the host part of the address might be two bits or 3 bits or 4 bits or whatever. In IPv6, it's going to be 64 and should always be 64. And we'll see an example of subnetting pretty quickly. All right, the types of unicast addresses are something that you have to get pretty much nailed down. The global unicast address is what is equivalent to a public IP address, a public IPv4 address. That is what an ISP would assign to your organization, a GUA. And they'll usually, like I said, give you the first 48 bits, and you do whatever you want with the next 16 for your subnetting, and then the last 64 are your host interface addresses. So that's your public address. Link local addresses, anytime IPv6 is enabled on a device, that interface has to be assigned a link local address. Typically, if you don't assign it statically yourself as a network administrator or just administrating a host, it will assign it itself. It'll give it, they always start with FE80. So link local address, we did hear that in IPv4. It has a really very different function in IPv6. It actually is used for most communication within a LAN. But you did hear link local address in IPv4. Do anyone remember under what context link local address was talked about in IPv4? A PIPA, yes. So the APIPA address that gets automatically assigned if a host is set up to get its address through DHCP, but a DHCP server isn't available, it will automatically assign itself an APIP address. That starts with 169.254. Well, the purpose of that, it was just, Windows kind of started with that 169.254 business so that you could start up a Windows computer, and if there was, even though there was no DHCP server on there, it could still communicate with other devices in the LAN because, the auto-configured a PIP address. But they can't be routed, period. They can't go, it's not just not out to the internet, they can't be routed internally either across your own routers. That's the same thing with FE80 addresses. Link local addresses are only communication within the broadcast domain, meaning within the LAN up to the router interface. They can't be routed across that router interface. And they're not meant to. So every device that's got IPv6 enabled will assign itself an FE80 address. It's usually like FE80::, and then the last 64 bits will be the interface address, which for the most part looks a lot like the MAC address, at least on some devices. Okay, and then the last is called the unique local address. This is actually what we're using in here, just because I decided one day to enable IPv6. And I think I might disable it because it causes more confusion than anything else. Unique local addresses are equivalent to IPv4 private addresses. They can be routed within an inner network, but cannot go out to the internet. They are meant, I think that the whoever, the people that wrote the spec for IPv6 created, reserved those addresses FC00 through FDFFF for the purposes of companies just experimenting with IPv6. Because the most current thought is that link local addresses are always going to be there. Every device has them. But once you go to IPv6 for real, you're going to use global unicast addresses. If you want to play around in your internetwork with unique local addresses with IPv6, that's what the purpose is. But they're not going to be like private addresses in IPv4 where you use NAT to allow those addresses to go out onto the internet. I won't say there is no NAT for IPv6, but it's not supposed to be used. You shouldn't use NAT in IPv6. You should have global addresses in your inner network and just configure your firewalls to disallow, inappropriate traffic. So no NAT in IPv6, or at least it should not be used. It does exist as a possibility though. Okay, so, we'll look more at some of these as we go along. But do remember, FE80 is always link local. I think it can be FE80 through, it doesn't actually say it there. It can be FE80 through something like FE8F or something like that. But FE80 has become the standard. You won't see any other, unlikely to see other types of link local addresses besides FE80. And then global unicast really can be just about anything that isn't reserved. Anything besides this or this, and there's a few other reserved addresses for like multicast. But there is actually, they pretty much have only released a very small portion of the global unicast address space, like 2001 and 2002. Okay. PowerPoint did that again. Okay, so like I said, the unique local is kind of like the private addresses can't be routed. And for the most part, you know, it's really just meant for dabbling in IPv6 until you're ready to actually use it for real. So see this note down here, it says, many sites use the private nature, meaning they can't be routed, of the RFC 1918, which is the unique local addresses, to attempt to secure or hide their network, just like private addresses are used sort of like that in IPv4. That was not the intention, okay? So that's what they're saying there is, you don't do it that way because that's not the purpose of IPv6. You want to have end-to-end communication, public address to public address. But it's, people still might do that. Okay, so globally unique addresses. The in globally unique addresses, you're gonna, the first 3 bits are gonna have the pattern, or the first 4 bits are gonna have the pattern 001, 0 or 0011. And that tells, you know, the rest of the world or the router that that's a globally unique address. So basically 2000/3, that just means that the first 3 bits are what makes it a globally unique address. All the rest of the bits can be whatever. But if the first 3 bits are 001, then that makes it a globally unique address. And that basically means it's a 2 between 20 and 2F in the first 8 bits of your IPv6 address. Okay, but it's right now they've only allowed 2 or a value of 2 or a value of 3. So right now, the entire IPv6 address space, global or public address space, is, you know, only 1/8 of it has been released by the holders of those numbers. All right, so from 2000 to 3FFFF is what's currently available as globally unique, and they'll release the rest of it when needed. And it may never be needed because that's still a lot of address space. Oh, let's go back and look at that middle part. So the first 48 bits, which represents this purple part. Zoom people. The first 48 bits annotation again, or what? Oh, okay. So the first 48 bits are what's called the global routing prefix. Again, that is what your ISP, if you were a company that said, we're ready to go IPv6 on the internet, they will give you the first 48 bits of your address. You can then do whatever you darn well please, subnetting wise, with the next 16. So basically you have from 0000. So this subnet ID can be 0000 to F. And that's all there is to it. There's no subnet mask or anything like that. So you could, whatever this global routing prefix is, doesn't matter. You want a subnet, your first subnet could be 00000. Your second subnet could be 0001. Your third one could be 0002, 0003, all the way up to FFFF. So how many subnets can you have? And this applies to just about any organization. So just about any organization can have up to how many subnets? How many does that give you? From 0 to FFFF.
Within powers of 10.
No,
16 to the
it's
fourth
2 to the 16th, 16 bits.
Right.
So 2 to the 16th is 65536. So 65,000 some subnets. It's a lot of address space. All right. So, there might be some companies out there, Microsoft and some of the huge ISPs that might have 65,000 subnets, but, it's more than enough address space because, because the address space is so huge, we don't have to worry about dealing with, parts of octets and stuff like that. You've got that entire 16 bits to do whatever you want with. The interface ID stays 64 bits, so that never changes. You don't have a host field that's going to be sometimes 2 bits, sometimes 8 bits, sometimes 16 bits. It's always 64 bits. So when you think about it, you could anybody that gets a globally unique or a global routing prefix can have 2 to the 64 hosts on 2 to the 16th subnets. So that's a lot of address space. You shouldn't ever have to worry about conserving addresses. So what people will do with that subnet ID is they'll make it mean something. So for example, if this was by college, the subnet ID, if things worked out that way, well, they could even do stuff like 1901 for, that's 4 digits. 1901 for building 19, first floor. 1902 for building 19, second floor. And then if they needed to make it, even smaller than that, they could, take that and just break, 19 and then additional numbers for each classroom or something like that. So, you could start with just 0 and then just keep adding 1, 2, 3, 4, 5, and that's your subnetting scheme. But it would make more sense if you use the idea, the thought that you've got all this, these hexadecimal numbers to, represent something that they mean something. You could even use part of a area code, for the different cities that your organization might be in. So you could use the first 3 digits of the subnet ID would be the same as your area code where your branch office is. And then the last digit would be the individual subnets within that branch office. So, you could come up with some pretty, meaningful schemes for your subnetting, which you can't do with IPv4 really. Okay, so like I said, global routing prefix is going to be 48 bits, subnet ID 16, interface ID 64. So it says in most cases, strongly recommended that /64 subnets be used. That leaves open for the idea that you can do something different, but everything I read is don't bother. You just make your life hard if you deviate from what most of the world is going to do. All right, so while we, spent most of our time with IPv4, dealing with subnet masks and how to subnet, and IPv6, I just showed you, that's all there is to subnetting. What the challenge of IPv6 is just keeping straight all these different address types and what their purpose is. So FE80, and it says /10. So really only the first 10 bits have to be, F and E, and then the next 2 bits would be, the up to from 80 to FEBF. But convention says just make it FE80/64. So basically your link local addresses should all look like this. FE80 : and then /64, which basically means that after this FE80, the : means that there's going to be 3 fields of zeros. So it's going to be FE80 0:0:0, and then the last 4 fields of 16 bits are going to be your interface ID, your host address. Okay. So again, the link local address is automatically assigned by like Windows. So you've seen that already. If we bring up a command prompt. We see that each interface has been assigned its own interface address, its own link local address, I should say. Turn off this. So these addresses up here, the FDs, those are coming from my router, but the FE80s for each one, this here FE80, that is automatically assigned by Windows on each interface. But basically, it's FE80 : and then the interface, you know, that's your 64 bits right there. That's a random number generated by Windows. Okay, so that's how Windows does it. For the interface ID for the link local, it uses a random number. Now, Linux and other devices use what's called EUI64, which we'll see in a second what that means. But Windows does it like this, although you can tell Windows, there's a command to tell Windows to use the EUI64 method, which I kind of like better because you can see what the MAC address is in the IPv6 in the link local address, but Windows doesn't do it that way. They use just a random value. Now you can assign a link local address if you want and prevent the device from automatically creating a random one. It's up to you. Most people for hosts, they let the device create their own. Administrators will usually give the router a static address. All right. Next slide. Static configuration. Let me get rid of that writing. All right. So this is how you configure IPv6 on a router, first with a globally unique address, just IPv6 address, followed by whatever the global routing prefix is, first 48 bits. And then the next field is your basically your subnet field. And then the last part of the address is the interface ID. So what they've done here, and this is kind of, you know, you don't have to do it this way, but they're basically just assigning : : 1. The : means a whole bunch of zeros, and then the last field has the value 1. But you can do anything you want after the routing prefix. For the after the subnet part of the address, then these last 64 bits can be anything you want. It's just, you know, they're making it easy here, : 1. Yeah.
On the certification exam, are they always gonna just want it in the uncompressed form or in the compressed format of IPv6?
Well, you probably won't have to write any addresses down unless you can, unless the problem requires you to configure addresses on a router. And the router will take it either way. This is, you know, the shorthand form with the colons and no leading zeros. So you could do it either way. And on the certification exam, it will take it either way as well. Okay. So manually configuring on Windows, same thing. You just go to the IPv6 properties and type the address in that you want. Okay, so this SLAAC, we're going to see what that means shortly, but that's basically, you know, the automatic configuration of your IP address in IPv6. So there is such thing as DHCP v6, but you can also just let IPv6 self-configure everything without a DHCP server. All right, so that was a globally unique address. To configure a link local address, you have to actually say link local at the end. To me, they could have, if it starts with FE80, it's a link local address. I'm not really sure why Cisco router requires the keyword link local, but it does. So I think if you leave it out, it'll say that this requires link local. It's like, well, then why don't you put it in? I don't know. I really don't understand that, why they required you to put that in when if FE80 right there spells it out that it's a link local address. But anyway, they do. So you got to remember to put that in there. All right. Now, here's one thing. I don't know if there's going to be an example. Link local addresses can be, as long as you don't use the same address on multiple interfaces where they're in the same LAN, physical LAN, you can use that FE80::1:1 everywhere, like on at least on one interface on each subnet that you want. Because since they're only local, this router one's, you know, gigabit 000 will never talk to another router's gigabit 000, as long as they're not on the same link together. So you can reuse link local addresses when you're assigning, if that's what you want to do. It's probably not a good idea because it might confuse things, but you can because they never talk to each other, so they wouldn't be considered duplicate address. Yeah, it says that in the note here. Same link local can be configured on each link as long as it's unique on that link. Okay. However, it's common practice to use a different one on each interface. All right, so this is where things get, you know, the other hard part about IPv6 is remembering all the different message types and the way that addresses can be dynamically assigned. So this SLAAC, stateless auto address configuration. There's basically three ways that IPv6 addresses can be automatically configured. SLAAC without using any type of DHCP server. In other words, the way that works, and I think we see it in the next slides, but real quick, if it's just SLAAC, stateless auto address configuration, that means the router on the network sends the prefix to the host, and the host just takes that prefix, you know, which is the first 64 bits of the IPv6 address, and uses its own interface address, puts them together, and that's its 128-bit dynamically configured address. So that's one way. The other way is with stateless DHCP v6. In that case, the DHCP server will be used to give, so the router will still give them the prefix, the first 64 bits of the address, but then the DHCP server will be used to give them other information like DNS servers and domain names and things like that. So it still doesn't keep track or have a database full of addresses when that method is used. It's the DHCP server is only used for those additional addresses like the DNS, domain name, and maybe some other types of addresses that you need to configure on your client devices. So in that case, again, whenever SLAAC is being used, the whatever router responds with the prefix, that's your default gateway. That will be the device's default gateway automatically configured. So whichever router responds. So what happens is a host boots up. So right now for IPv4, we've learned that when a host boots up and it doesn't have an address, it sends out a broadcast to a DHCP server saying, hey, I need an address. And the DHCP server responds with an IPv4 address, default gateway, DNS server, or whatever else. Well, with v6, it's the same idea. The host boots up and sends out a router solicitation ICMP v6 message. It's a multicast because there's no broadcast. And any routers that are that hear that will send out a router advertisement message, which will usually contain the network prefix and prefix length. The default gateway address, again, will be the router's address, the router's link local address. And the DNS address and domain name can be sent by the router, but more often it's going to be sent by a DHCP server. And then finally, the last way is just like IPv4 DHCP. The host contacts actually it sends out instead of a broadcast, an all DHCP servers solicitation message. It's a multicast. And it'll tell the DHCP server, I need my address, and the DHCP server will give it the prefix, possibly even the interface address, and all the other stuff, default gateway, DNS address, and domain. That last way is probably the least, the way that you don't want to use, just because it means more work for you to set up a DHCP server, and then it's got to be managed by the DHCP server. So the most common way, I think, is going to be the middle way, where you want the DHCP server to, handle some of the stuff like the DNS addresses and the domain name. So, but everything else will be handled by the router. Probably a lot of places will do just SLAAC and do away with DHCP altogether. So it all depends on, what your requirements are. Okay, so that's router solicitation is what the client sends, saying I need an address. Router advertisement is what the router sends back. Now there's more to it, unfortunately, because the router advertisement will tell the client how it should be getting its address. Which one of those three methods it should use. Get rid of the writing. Okay, so again, the EUI 64 or random, the EUI 64, I don't remember if it's described in here, so I'll describe it now. The EUI 64 method of self-assigning an interface ID, the last 64 bits of your address, is basically you take the interface takes its MAC address, first 24 bits of the MAC address, and then it inserts something, what the heck is it now? Something like FE00. Well, I think it's in another slide, but it inserts 16 bits and then the last 24 bits of its MAC address to make up the 64. So that's what EUI 64 is. It's just first 24 bits, a pattern like FE00 or something similar, and then the last 24 bits, put them together to give the 64-bit address. Windows doesn't do that by default. Linux does, but you can tell Windows you want it to do EUI 64 if you really want. All right. All right, so this is how it works. So a router advertisement has, so when the client sends out the router solicitation message, it's, you know, basically a multicast that says, hey, you know, it's addressed to all routers multicast. And it says, I need to know how to do my address, my IPv6 address. The router can instruct it to use SLAAC or SLAAC with stateless DHCP or just DHCP by itself. And that's what the administrator has to configure on the router is how should I get my address? And there's just some codes that you know, some commands you put in the router to tell it. So the router that responds to the router solicitation will respond with a router advertisement. And if it tells it SLAAC, then it says create your own IPv6 address using this prefix. The link local address of the router will be included in, well, dang it, will be included in the message. And that's what the device will use as its default gateway. So it'll use the link local address of the router, the FE80 address. And then if the router tells it to, the client will then contact a DHCP v6 server to get additional addressing information like DNS, domain name, other stuff, boot P server or whatever is needed. Okay, so that's how most of them are going to work that way. Okay, it can also tell it to use stateful only. Stateful only says, I'm not going to give you any information except you will use my link local address as your default gateway. So if the router responds, the device will use it's the link local address of the router as its default gateway, but then it'll contact a DHCP v6 server to get all of its address information. Like it'll get its the first 64 bits of the address, and most likely that's all it'll get is the first 64 bits, but it could also hand out the interface address as well. Most likely though, the interface address will be auto-configured either through EUI 64 or stateless. All right, so EUI 64 protocol. Did I get that right? It's still not telling us 16 bits that inserts in there. That's okay. So when the router advertisement message is either just plain old SLAAC or SLAAC with stateless DHCP, the client generates its own interface ID. If it's DHCP v6, the DHCP, just like with IPv4, the DHCP server actually sends its interface address as well. All right, so all depends on what the router tells it to do, which way to use. All right, so yeah, FFFE is that 16 bits it inserts. It also flips one of the bits. So this FC in the MAC address becomes FE. I'm not really sure why they did that. I think I might have read a reason a long time ago, but I can't remember. So the MAC address, the first 24 bits are used. The 7th bit is flipped from a 0 to a 1. Actually, if it's already a 1, it'll be flipped from a 1 to a 0 as well. So it's basically, flipped from whatever value it is to the other value. FFFD is then added on to the first 24 bits, and then the last 24 bits of the MAC address round out the 64-bit interface ID. And that, to me, that method is better because you've got a relationship between the host and its EUI64 address. Whereas with the randomly generated ones that Windows does, you can't look at the interface ID and know anything about where it came from. So, but whatever, that's the way that Windows decided to do it. All right, so just to be sure, even though that interface ID is 64 bits and the likelihood that there's going to be a duplicate is very, very, very small, because first off, the MAC address, if it uses EUI64, should be unique. But nonetheless, there is that small chance that 2 Windows computers could create the same address using the random method. And so Windows will do a DAD, duplicate address detection, or any device using randomly generated will do the duplicate address detection. So it's basically, it sends out a neighbor solicitation with the address that it configured to see if anybody responds. And if somebody responds, just like with IPv4, if somebody responds to the ARP, then they know that that address is already in use. So that's what duplicate address detection is. It's basically just doing a an all nodes multicast with the address that it configured for the interface. And if somebody responds, then that means it's in use and it'll generate a new one. All right, almost getting close to the end here. All right, so multicast addresses. There's a whole bunch of special reserved multicast addresses in IPv6. They'll always start with FF. And then after that, only the first 8 bits are have to be FF. And then the next 16 bit or 8 bits can be anything. And so basically there's 256 possible reserved addresses. So FF02::1. So FF02::1 is the all nodes. That's basically like a broadcast because all nodes will read that read that message in and see if there's anything to be done with the message. And then FF02::2 is the all routers. And then FF02::1:2 is the all DHCP servers. So those are 3 common reserved multicast addresses. So whenever device boots up that's configured with IPv6, it's going to send out an FF02::2 ICMP v6 message looking for, it's a router solicitation looking for its IP address. And then if the router tells it use DHCP, then it will send out this other one. All right, the solicited node multicast address is basically when is like an ARP. So a solicited node multicast address, it's the all nodes multicast where the last 24 bits are the last 24 of the message are the last 24 bits of the IPv6 address. So basically it sends out the FF02::1:FF, and then the next 24 bits are the address that it's looking for. And if it gets a reply, then it knows that that address is in use. If it doesn't get a reply, then the address is not in use. All right, subnetting, like I said, you use that middle field between 48 bits and the 65th bit. You got 16 bits to create your subnetting scheme, and there's nothing to it. That's all you got to do is just create a unique value, and that's your subnet. And my PowerPoint died again. And not only did it die, it lost its place. Yep. So this would be the most basic subnetting example you could do. Start with 0 and just keep counting. All right, each one of these will be a separate IPv6 subnet because the first 64 bits of the address are the network ID. So just as long as 1 bit difference, then it makes it a unique subnet. So that's a real basic way to do it. And this would be an example of configuring a router with 3 subnets. Each interface gets a separate subnet. Something went crazy with my turn off annotation. Turn it back on, see if that helps. Yeah, so that's the subnet field right there. So that would be a simple way to configure your interfaces on a router. Just use whatever, this is the Neticad's globally unique address or prefix that it gets to use in all of its examples. The first 48 bits are that 2001 DB8 ACAD, and then the next 16 bits is the subnet. And then the last 64 bits is going to be 3 fields of zeros, and then you just put 1. So, and then your other routers, if you were doing like a point-to-point, if this router was connected to another router through that interface, you would just give it 2 as the interface ID. So, yeah, that's all there is to it. And thank God we got through it. Okay, so as you can see, IPv6 subnetting is not an issue. The only thing you have to kind of learn really is all the address types and their purpose, and then also the Um, You know, at least those three multicast addresses, I think those, you might be tested on those. So just kind of try to get those memorized. But really, it's mostly going to be the address types. The you know, if you see FE80, you need to know that that is a, what type of address? Link local. And if you see something FC00, FD00, what is that?
Is that a global?
No, that's
It's the unique.
unique
Unique
local,
local.
which is like a private. And then 2000 through 20 through 3000 is a globally unique, or actually between 2000 and 3FFFF are the globally unique range of addresses that are currently available. But really in you know, eventually, once they start allocating them 4000 through, because you don't want to get into the Fs because those are multicast, but basically through EFFFF will be the whole range of globally unique addresses. Unless they do, you know, reserve some of the others for some purpose, but so there's huge address space, and they've only released 1/8 of it as of now for the public facing devices. All right. Have a good weekend. Monday, we'll do those 2 labs. So Zoom people, you don't need to Zoom in. And then the following week after Thanksgiving, we'll basically be finishing up. Have a good weekend. Just finish.